I'm going to start off by introducing Supapon Kulthinee, Dr. Kulthinee, I should say, or Tabby as she'd like to be known. Tabby started her career out in Thailand to do her perfusion studies before she went on to do a PhD, and she's now based at the Vanderbilt University. She specializes in renal physiology. She actually runs a social media site, which is Physiology for Perfusionists, which I believe has got over 2,000 individuals that have signed up to this. So she does a lot of mentoring, and she's a chair of the division back in Thailand as well. So really, this is the ability to learn from somebody who crosses both the physiology and the perfusion boundaries. So it's a huge amount of pleasure to welcome Tabby up to the stage, please. Oh, and just because this is all at AKI, what we're going to do is do a panel discussion at the end. So we're going to do the presentations. If you could hold your questions to that point, we'll have the three speakers together.
Thank you, Alicia. Thank you, Alicia. It's just a nice introduction, and I'm super excited as a first speaker. But good morning, everyone, and it's a great honor for me for being here. My talk today, I will cover I'll spend a half of my life for do the research in renal physiology, specifically in preclinical research, which I was showing you, and currently I'm working on some of the differences in renal function. And also I'll set up and go to, show for the clinical trial, and I hope the end of my talk will give you and spark for some idea for our perfusionists working at the bedside. All right, let me, I don't have any disclosure for my talk. Let me, just briefly about me, before I'm a physiologist for today. I was a perfusionist of graduate in 2004. And after that, I worked as a perfusionist for 8 year experience in Thailand. And in Thailand, we work for both pediatric and adult. That is my experience. And I have so many questions, gain more and more questions during I was a perfusionist. And then my boss said, okay, you have so many questions. You go to school, you please go back to school. And I decided to do the master and PhD in physiology. And I choose one of the most exciting for me for my research project for the dissertation for master and PhD. I'll do the cardiac ischemia reperfusion injury, because my first question is just about when the heart stops. We have the cardioplegia, and we all know about the cardiac ischemia reperfusion injury. I'll show you just briefly. In my study, I use the asphyxia technique to induce cardiac arrest. I insert the endotracheal tube to the rat, and then to clamp the tube, and which is induce cardiac arrest. Before I'll do the experiment, my idea is that life is kind of mathematics. Maybe I'm wrong, but I'm thinking. I just think when I start to clamp the tube, which is induced for asphyxia, it should be start going down, decreasing the blood pressure. That's my idea. But I want to see that. Let's say on this, when I start to clamp the tube, you can see the blood pressure go higher, rapid increasing. This is from compensatory mechanism, like activate sympathetic. But it just for a while, and then it's rapidly decreasing. And then I release the clamp, let's say about the 50 millimeter mercury. It starts rapid increasing, and it's not returned to baseline. It's going up and up. And I just realized that wow, life is not mathematics. We have so many compensatory processes happen. And how about the kidney function? And then I'll look at the renal sympathetic nerves activity at that time, and I found it's different. It depends on the treatment, but I will not go to the detail for now. But just briefly to showing you why I'll start my journey in renal physiology. And as soon as I earned a PhD, I do such a crazy thing. I email with a long email. Maybe the whole page of the A4 with a very long email to a professor in Tulane. he was a past president of American Physiological Society, and he was a chair. And I introduced myself. Dear Dr. Nawar, I am a perfusionist. I don't even know he knows perfusionist or not, but I'm very interested to study in renal physiology. And he got back to me on that day. He said, when you want to come? And that's my journey begin in renal physiology. I'll choose the project to look at the renal autoregulation, specifically when response, because my question on that, let's think about the pulsatile and non-pulsatile, which is the question for all perfusionists. How about the renal autoregulation if you fall by pulsatile or if you fall by non-pulsatile? It is the same or different. And I want to see it by my actual eye. That's my idea. And in his lab, he has the equipment we call the JMN technique, which is allow me to visualize, and I can see by my eye how it responds. And I'll show you. I have the actual video. All right, let's go to renal physiology together. As we all know, the smallest part, but it's a functional part in kidney, is we call the nephron. And I'll go back a little bit. Okay, and at nephron, this part is a very special one. But go to the renal afferent arteriole, and then it's formed to capillary, but for the kidney, we call the glomerulus. And I extend this picture. This is from Dr. Nawar. Right here is renal afferent arteriole, and then it's go from for the capillary, but we call the glomerulus. So as the capillary, it's just an endothelium, so it's very risky to damage. So that's why renal afferent arteriole have a specialized for renal autoregulation to control the pressure. You need a very good to control the pressure to protect your glomerulus, and also you need to keep constant for the urine flow. That's the job. So that's why we call the renal autoregulation. And how it's specialized, I'll show you for very nice study from the group. When you decrease blood pressure, systemic blood pressure, that means you decrease renal perfusion pressure. When you decrease pressure 100 to 60, or even a little bit higher to 80, you can see the renal afferent arterial diameter is increasing when you decrease pressure, and the diameter is go further decreasing when you increase pressure. This is showed renal autoregulation. And I'll show you for my experiment for the video record. It's just a bit slow. I'll use the JMN technique, and this is the afferent arteriole, and this is the glomerulus. And then you keep eye on this. And this is the renal afferent arteriole, and that's the glomerulus. And then I flow by non-pulsatile. I keep the pressure about 100. And this is for the blood, and you keep eye on this. And right now the pressure is about 100. Yeah, it's right here. It's renal afferent arteriole. And when I increase pressure to 140, you can see it's rapid to vasoconstriction. You can see its movement. You can see its movement, and it's very quick. And the one that I'm showing you right now, I do the non-pulsatile flow, and I have the answer to myself. Even you pulsatile or non-pulsatile, the renal autoregulation is precise. It still works. But this is on the temperature, that's just normal temperature, 37. I haven't had a chance to compare if you go by hypothermia, how different. It's still the question. I also want to do this. But I'm showing you, once again, even non-pulsatile or pulsatile, the renal autoregulation is still working. And how it works? Because at the renal afferent arteriole, they have the receptor. One of the important receptor we call purinergic receptor, which is have two subtypes, P2X and P2Y. And my research, I focus on P2X. I was showing you when we block the P2X, when you increase pressure and you block the P2X, you cannot make the vasoconstriction. That is clearly shown it's happened because it's activated it's controlled by the purinergic, which is a P2X receptor. We also do in the knockout mice when we delete the P2X1 receptor. You can see it abolishes the vasoconstriction effects, and that's a part of my research project and in Tulane. And once again, I also test when I block the P2X1, when I increase pressure from 100 to 140, it also show the vasodilation, which is the main effect from the P2X1 to control the renal autoregulation. And one thing that I want to emphasize for now, we as a perfusionist, we also have a question: how about the hypertension patient? And we compare to the a normal hypertension, normal blood pressure, and how about the hypertensive patient? Most of the study they show the renal autoregulation is impaired. It's like a light ship. You need a higher blood pressure for the autoregulatory length for the hypertensive patient. I also found that actually I did not find a significant between normotensive and hypertensive in rat study. However, I found a similar trend for the renal autoregulatory impairment in hypertensive condition. So that's what we need to keep in mind. I mean, there are different range for the hypertensive patient. And that's a part in Tulane. And currently I'm working in Vanderbilt. I'll focus on purinergic again, but on the P2Y. Sorry. Right now, I'm working on the P2Y2 receptor, which is expressed in so many areas in several areas in the kidney. And why P2Y2? I'm showing you. P2Y2, the receptor, when it's activated by ATP, we're familiar with the ATP in intracellular, like an energy source. Actually, ATP can release to the outside the cellular, and also it can activate the receptor. And when activate P2Y2, it's promoting sodium accretion. The important one is that when we compare in female compare with male, this is the study in rat, female compare with male, and compare with female removed ovary, which is we induce the deprivative of estrogen or ovalectomyelin. We found that ovary intact female rats have a greater renal P2Y2 mRNA expression that we found, which is show different. Let's show the sex differences for the P2Y2 mRNA expression. And to answer about the question, what's the underlying of the difference? Dr. Koha, she used the medullary collecting duct and treat with the estrogen, and you can see it's response to those responses. The high dose for estrogen, it show increased P2Y2 mRNA expression, which is show something. I mean, show the renal function in male and female. We have some difference for currently that we found. Yes, I'm talking about the estrogen, and also we look at the estrogen receptor. There are several subtypes of estrogen receptor, but the novel one is G protein coupled estrogen receptor 1 or GPR1. And we found that GPR1 is specific for in female. When you activate the GPR1 for the kidney, it promotes sodium accretion, which we call natriuresis, and also it promotes diuresis. But it happens specifically for female. And again, we remove the ovary. That is the ovalectomyelin. And then when we activate the G1, we found it, after we activate the G1, we found it's increased sodium accretion. So that's kind of interesting. I mean, for us, for thinking about the sex differences. And that's now, I'll showing you for this pathway before, and then I'll show you for the GPR1 when we activate. It does get involved for lowering blood pressure or not? That's also the question. And yet, that's my current project. I have the hypothesis. that if we activate the GPER1 or GPER1 will regulate the renal P2Y2 ENaC signaling and should maintain blood pressure. That's for the hypothesis. And to test the hypothesis, we use the two models. One, our study in the knockout, we delete the GPER1 gene, so that means no GPER1 receptor in mouse. And we found compare in female and male. We found P2Y2 mRNA expression higher in female compared to male. And when we knock out, delete the gene, which is clearly show it decreased P2Y2 mRNA expression. And this is the set differences in male and female for P2Y2 mRNA expression. Again, that's I'm showing you. And also, we also found the same thing for ENaC, which is the channel for inhibit the sodium. And one of important and exciting for me, you just only remove the ovary from female, you can see it's increased blood pressure. And when we challenge them with the high salt, it goes further for increased blood pressure. And when we activate the GPER1, or let's say we treat with the GPER, we activate the GPER1, it's prevent the high blood pressure, which is show the, when we activate the receptor in female. And also, we also showed, we found the differences in connexin 30, which is released for the ATP. We also found when we activate the GPER1, it's increased the ATP level in female. This, once again, also in rat, the same in mice, we found the increase in P2Y2 mRNA expression, but we did not find the differences for ENaC activity. But to sum up for you for now, in my current research project, we found sex differences and underlying by estrogen and also estrogen receptor that we found. But all this, that is not just only my study, zero study for now, we found the sex differences in kidney function, between male and female, specifically for sodium excretion and how to so many protective effects, and I'll show you which is involved in CPB. That's, the part of physiology, the part of science, the part of my job. Also, let me thinking about a part of me, a part of my professional career life as a perfusionist. I'll go back to my first question about the ischemia reperfusion injury. And let's say, if we study in ovalectomyelin, if we focus in female, how would it be? And I found, for the review literature, in the model renal ischemia reperfusion, which and induced kidney injury in ovalectomy female labs, when they treat with estrogen, it can prevent the kidney damage, which is one of the studies show that. And let's think about the inflammatory response, which is, we all know is happened in CPB, and I very appreciate in this study. They show that in the study in rats, in CPB, and you can see the plasma interleukin 6, which is the marker for inflammatory. In CPB, it increased about 4,000-fold for the interleukin 6. And then the study, when you treat with the estradiol, which is the estrogen, when you treat with estrogen, and you can see it decreased interleukin 6, which is one of the studies show, and also it decreasing for the KIM1, which is good for showing the renal, for renal protection. And also, once again, and this one is very interesting for, if you do hemodilution, hemodilution alone without CPB, let's say your experiment just infuse saline and make hemodilution. And that show increase the neutrophil deposit and also show inflammatory response. And if hemodilution with CPB, and that's make it's more get worse, it's increasing for the neutrophil deposit. This is, they are showing for that. And the experiment, the trial, but just small trial in human, they treatment with estrogen in male, but just small number. and then do cardiac surgery for, the CABG. And after CABG for 6 hours and 20 hours, it showed decreasing for leukocyte compared to control, which is shows some protective effects for the estrogen supplement also. And one that I want to point out, we kind of familiar with angiotensin 2 when we block the AT1 receptor and it shows vasodilation. This is the classical pathway, and we all know this is they develop for the hypertensive drug. It's, for example, like omisatan, which is the AT1 receptor blocker. That's a classical pathway. And the new pathway that they found, beside the AT1, they found the AT2 receptor, which is kind of counteract for the AT1 receptor. If you activate AT2 receptor, it shows protective effects. And it's exciting that AT2 receptor is greater expressed in female compared to male. It's kind of show you have the more protective effect for female. That's the data. In preclinical data in animal study that's showing. And also in human, they also found plasma renin concentration, the gradient of plasma renin concentration, which is a high risk for AKI. And it makes sense to thinking about the protective effects for AT2 receptor, which is another pathway for female. So that's I'm showing you for the preclinical data. It's trend to be we have the protective effect for female. We have some different mechanisms underlying for female. But for the clinical data, the definition, the guideline from the KDIGO for the AKI, that's we currently use the guideline. That's in the human data, and you can see, we all know CSA AKI is a high risk. It's happening about 30% of the patient after cardiac surgery. And it's getting more and more. It depends on age. In H1, you're more high risk for the CSA AKI. And also, they point out too, if you are the female gender, if you are the female, you are high risk for CSA AKI. But that's different from preclinical data, because preclinical data, we found the protective effects. That's led the question, in female, premenopausal and postmenopausal, many effects for the result for CSA AKI, and also need to be further for the study. And I'll show you one just recent published in last year. They compare between young group and old group. The age cutting point at 60 years old. Compared to male and female, actually CSA AKI, this is not different compared between male and female in all their group, in all young and in old. But what they found in all female, in the old group of female, you have high risk for longer period stay in hospital. You kind of high risk for longer intubation time that they found. And next one that I want to emphasize is that in one of animal study, look at heart, look at intestine, and also for the kidney. Kidney is less tolerant for anemia, less tolerant for hypoxia compared to another organ. And the study in human in 2013, and they found that female have a higher tolerance for low hematocrit. That's the fact, but that's a long studies ago. So that's mean that if you are female, you kind of high tolerant for anemia. And again, perfusionists, we all know for the female, we have the lower hematocrit level when compared compared between female and male. Female has a lower hematocrit. That's when I read the paper. That's great. I have the more tolerant. But the recent publication, they compare between male and female again. They did not find a difference for the CSA AKI and the tolerance for the hematocrit. But the point that they found, you need to be very concerned for the hemodilution for both sex. This is the main effect for the AKI. And I do agree. Why I'm saying that? Why I'm saying I do agree. When I did postdoc at Brown, I work on hemolytic shock in mouse model. We do the hemorrhage and keep the blood pressure about 30 millimeter mercury for 1 hour, and then we do the resuscitate. If you resuscitate by linker or resuscitate by bath, for the whole body of the animal, both can increase blood pressure. They are survive, but they are different. For the time for maintain the blood pressure, when they return blood pressure to 70, they both can return to 70. Even you resuscitate by linker or you resuscitate by bath, they return to 70. But the time for hold the 70 is different. It's go down very quick if you resuscitate by linker, but it's the longer time. We order preparing for the manuscript and hope to submit soon. If you reperfuse by the whole body, you have the longer time to maintain the blood pressure, which is I try to emphasize. Yes, we all know we should avoid the hemodilution, and from my experiment, I confirm with you once again, we need to very, very concern and avoid for the hemodilution and also for the study. So I go to my conclusion for my talk today. I'll show you for some evidence data for the human. I show the protective effect for estrogen, but we need to concern for female before premenopause and postmenopause. So they may different for the kidney protection for themselves. And also right now, still now female sex is still classified as a high risk for CSA, AKI. We also need more for look at the data to see how the age affects for the result. And yes, of course, we need the further study for premenopausal and postmenopausal and see how different, how we can work on that and improve it. And lastly, personal, I did not do the study experiment just for female, but for my goal, that's for all sex, that's for all gender. We want to have the strategy even for perfusionists, for everyone, and strategy for all sex, but just directly for them, specifically for them to improve the quality of life. That's my goal for the study. I'm currently working on the CPB model in rat study. I kind of developed of my team in Thailand for now, and have but just a bit, and I hope I can update you more for the next meeting when I get more results and study for the sex differences in CSA, AKI. We also look at the kidney function and for the heart function after the CPB and the ECMO. And I'm going to my two last slides. My journey in physiology as a perfusionist would not happen without the opportunity from Dr. Gabriel Navarre from Tulane, who he allowed me to, you do what you want to do, that he said. You just do what you want to do. I said, I want to study renal autoregulation. You do that, he said. That's a very good opportunity. And also my team from Tulane and currently at Vanderbilt, Dr. Koha, who she was focused on sex differences and specifically the data that I'm talking for today. That's from her mentoring and also my team in Vanderbilt and for the research support. And it's just wonderful. Dr. Gabriel Navarre is here with me. Hey, Dr. Navarre. Well, thank you again for this very nice journey. And I'm from Thailand, beside of the world, over 20 hours for the flight time, and over 20 years my journey in physiology and also perfusion as a perfusionist. And thank you so much. I'm so happy to talking my side for sharing my professional career as a perfusionist and everyone here. And I believe that our love in perfusion bring us together. Thank you.